Some numerical calculations and the Draghilev method. Given the equation f of x and y equals 0 and the function g of x and y, solve the equation for y equals y of x and then obtain g of x, y of x, which is a function of x, and its derivative, g prime, which from multivariate calculus is g sub x plus g sub y, y prime. Now, if the algebra were well behaved, it's trivial exercise. However, what if it can't be solved algebraically? So you think, well, it could be solved numerically. For each given value of x, you calculate the corresponding value of y. Now, how hard would that be to do in Maple? And if not hard, just how do you do it? So what we're going to show is how to do it, and we're going to do it simply without any fancy Maple coding, because this was done in response to an emailed question from a Maple user not overly familiar with Maple. So while I was constructing this solution and preparing a response to this email contact who had sent, as an example, some rather complicated functions of f and g that could not be unraveled. And I kept thinking that in the back of my head, there's this thing called the Draghilev method, and you'll see here two different spellings. The original spelling that showed up on Maple Primes had no H over here. And then all posts after that said, oh no, it really should be an H. So this method first showed up on Maple Primes, and here's the link to where it first shows up. And it's a method for solving inequations in n plus 1 unknowns. This is the earliest reference, and since that, I think I've counted 42 additional posts about the Draghilev method. But if you search for Draghilev without an H, you'll see there are 8 posts there. And here's a link to a site that has the spelling with no H. And here's the Draghilev's name in Russian. And here's papers that he's written. No H. So whether there's an H or not, we can kick that around. But the method basically allows for the parametrization of all of the unknowns. Right. So if you think about a set of n equations in n plus 1 unknowns, theoretically, you can solve for n of the unknowns in terms of the n plus first, so that the parameter becomes the n plus first. But in the Draghilev method, each of the unknowns, all n plus 1 of them, are parameterized with some parameters, say t, and then by differentiation you form n plus 1 ODEs, and you embed them in appropriate initial value problems, and then you solve those ODEs, or those initial value problems, for each of the unknowns as functions of the parameter, and here I wrote down t. So this example that I was trying to explain to the person who sent me the email triggered this recollection, and I realized, wait a minute, n is 1. There's one equation. N is 1 number of equations, and there are two, n plus 1, there are two unknowns, x and y. Would the Draghilev method be of use in such a case? And so I'm going to explore that. To what extent is the Draghilev method useful, and is this notion of parametrization really helpful or not. So, how do you explore a question like this? Well, you make some examples. So, I have two examples, one where you can actually solve explicitly, and then one where you can't, and you've got to invent some numerics. So, in example one, I just wrote down off the top of my head some function that I figured Maple could unscramble. So here's my function f, and then I make up a function g, very simple, and then I draw a graph of f, and I use the implicit plot command. So here I've written down the implicit plot command that I've used. It's actually, the code is actually hiding behind this cell. I'll show once where or how you can get at that command. Um, it's hiding here in format table properties. And here, check this box, show input, and then you can see there's the command. You execute that command, you get the graph, and then when you hide the material in the cell, or the input in the cell, you get the graph. This function turned out to be interesting to work with. First of all, you have a relation. You don't have a function. You've got branches. You've got an upper branch and a lower branch. The branches come together somewhere's down here, and so there's a challenge of finding where that point is and so forth. So it was an interesting enough example to play with. At some point in the process, I realized I wanted to know this turning point where the two branches join. So I needed to compute the derivative dx dy and wanted to know where the derivative vanishes. The derivative dy dx would go vertical here. Derivative becomes infinite. So you go dx dy, and where it goes to 0, you got the turning point. So I'm using the implicit diff command. The function is the function of x and y. Y tells Maple that the x is a function of y. And then I used fsolve to solve the resulting equation. I don't have to put equals 0 because Maple assumes that, and you get an approximation to the turning point. Here I've used the solve command to solve explicitly for y, and I knew I could do that because I picked a function that the algebra was not daunting. And this is the upper branch because of the plus sign. And so I've graphed it, and the graph looks like it should. It's the upper branch. And here's the plot command, and the command is actually hiding behind that cell, and I've shown you how to find that. Having obtained y of x explicitly, I now want to plug that into g. So I want to look at g of x, y of x. Well, that's a rather simple thing to do because here's your y, and you have to square it. There's x squared plus y squared. Then I drew its graph. Again, plot command. Here's the plot command. I didn't hide the plot command in this particular cell. And this is what it's going to look like. So whatever the function g might be, that's what you're going to get. You're going to get some graph of g of x, y of x. Having obtained g of x, y of x explicitly, I want to take the derivative, get g prime. So here I'm taking the derivative. Now this symbol is an atomic variable because you can't assign to an object like that. So here, if you want to check for the atomics, go to View, Atomic Variables, and you notice you get this magenta color every place such a symbol appears. So there are some atomics hiding in here to make the notation more natural. So here's what that derivative looks like. Mathematically, it's got to be the same as 2x plus 2yy prime. Just as a reminder, because I was pointing this out to the person who asked the question, that eventually this is how you're going to have to get the numeric version of the derivative, because you've got a numeric expression for y, and you need a numeric expression for the derivative based on the numeric expression for y, and then you can put the derivative together this way. And then I graphed it. Just want to see what it would look like. Well, having obtained uh, an exact solution to this problem, I now want to do it numerically, and I've got something to check against to know if my numerics are going correctly. So I need to solve the equation uppercase F equals 0. How do I do that? Well, I use the roots command in Student Calculus 1 because the roots command will work either numerically or analytically, and here it's working numerically because that's what we're checking out, and it will give the roots in within a range. Now that range becomes important because if you remember what the function is, its graph is the graph of a relation. You get two values. If you pick an x and solve for the y, you're going to get two values. And so I'm limiting the number of roots that I get by giving this range in y. So I'm finding the solutions between this value of y and this upper value of y. And that's why I needed to know where the turning point was so that I could select pretty much exactly the upper branch. And so here's my function. Pick a value of x, call that a, put that into the function f of x and y, and then solve that for y using the roots command. So this is a function that returns the value of y, giving the value of x as an input. So check it. Does it work? So you plug in, for example, 0.1, and you get this number. Well, I checked it. That's the right number using the exact expression. And so I said, okay, can I graph this thing? So here is where I'm drawing a graph. Here's the plot command, and I get a graph that represents the upper branch. So I figured, okay, so far I've got a simple expression for finding y numerically, and it works. So now I wanted to know if I could uh, get the derivative g prime of xy of x numerically. And so I'm looking at this 2x here. Now I know I can do 2y because I've got an expression numerically for y, and I'm thinking y prime I could get with the fdiff command, and I realized this is x and this is a function of a. So I ended up having to do this, make a function 2a, call that z. And then I've got this derivative, yp or y prime, and I've got that by fdiff. And here, this is the syntax peculiar to fdiff. You look up the syntax, and this is what you realize you have to do. And these are the two things I want to put together to get the derivative 2x plus 2y y prime. Does it work? Can I draw the graph of that expression? So here's the 2x, here's the 2y y prime, and I want to graph that on this range, and I get this graph, and does it look like this one? And I was satisfied. Yeah, so it works. I think this process can be made to work uh, on other problems, and that's what I'm going to give a try in example 2. So let's tackle example 2. And in example 2, there's no exact solution, and you see what example functions were sent me by the person who originally emailed me. This was the function f, and this is the function g. And there's no way you're going to solve this for y as a function of x explicitly. What does this function f look like? Is it single valued? Is it a relation? So I graphed it. Again, I used the implicit plot. Here's the command that's hiding behind this uh, cell. It's single valued, at least on the range 0 to 4. It seems to have an asymptotic value here. So it's a reasonable function to tackle. So let's apply the numeric procedures that we worked out for example 1 and see how it goes. Okay, so we use again the roots command. You pick a value of x, call it a, and then make a function here where f represents y of x. Test it, get a number, appears to work. Draw its graph. Can you graph this thing? Yes, it works. Here's the plot command that's hiding behind this cell. That graph seems to reproduce what the implicit plot command gave us. So it appears that so far this is going to work. So now we want to create a function g of x, y of x, where y of x is given by the function that we created up here. So take g, and wherever there's an x, you put a letter a, and wherever there's a y, you put f of a. Does that work? So you test it. Here are some numerical experiments. These numbers turn out to be the correct numbers. Then I want to draw the graph of g of x, y of x. And the commands hiding behind here, I've reproduced here. It took a little bit of time, and I'm experimenting and checking that the graph looks nice. And I want to know, how much time am I really wasting here? Every time I execute this plot command, well, turns out it's around 22 seconds of real time. So this is how you test how long something is taking. You get the real time, and then afterwards the command is executed here, the plot command. You get the real time, and you take away the earlier real time, and that gives you the number of seconds that this plot command ran. So now we're looking at derivative, and we're going to obtain the derivative by looking at some calculus. Gx plus gy, y prime. Can we create such an item? Well, we're going to need a y prime, so let's use fdiff to get y prime, and I call that yp. And we've got to put all of that together. G sub x, partial with respect to x, g sub y prime. So I poked around and I tried this. Let's differentiate g with respect to x. So it's got an x in there, g dg dx. How about derivative with respect to y times y prime? Now, yp is a function of a, but it's a function, so I can use as the independent variable x. And then let's make everything in terms of a, because this function f is actually given in terms of what happens to the letter a. Did that work? Well, it produced this expression. It's a function. A goes to this stuff where x is replaced by a and y is replaced by f of a. And then I want to graph that. What does it look like? So here is the command for graphing that. I wrapped it in time real. Turns out it took roughly 25 seconds for this graph to be drawn. So every time I did an experiment to see, what little changes should I make to the graph so it looks nice, I was sitting here drumming my fingers on the desk 25 seconds. Well, it appears to work, but I have nothing to check this against, except in some of the other material that the original questioner kept sending to me, there were graphs that looked like this. So I said to myself, well, it appears that this stuff works. I didn't have to use unapply or make function. The arrow worked. Uh, I think I satisfied the questioner with the stuff that I put together for him. Well, now it's time to look at the Draghilev method. Here's the general case of the Draghilev method, because you want to get some idea of what's going on here. Well, you've got n equations, that's what these are, in n plus 1 unknowns. And as we pointed out earlier, you can solve for n of these in terms of the n plus first. But what happens in the Draghilev method is you parameterize everything. You introduce a parameter, say t, and you parameterize all of the variables as functions of t. And then you differentiate. And this is just the chain rule. df, dx, dx, dt. And you do that for each of the n plus 1 variables and each of the n equations. Now you need one more equation. So you need something for x n plus 1 dot. And it turns out to be this expression, and it's called, well, you can see it's a Jacobian, and they claim it comes from using Cramer's rule. Now, when you think about that, if you have a set of equations and use Cramer's rule, there's a denominator that appears. There's no denominator here. What happened? So this was a puzzle. I kept looking at this and saying, there's something going on here that I don't understand. And so that's why I had to break it down, take a simple case, take n equals 2, and just try to understand what's going on. Well, what do you do when you're trying to comprehend something in terms of multivariables? You make simple model, simple case. So let's look at the case where you have two equations and three unknowns. F1 function, F2 function. This is the chain rule, and this is what the third equation looks like. X dot equals this Jacobian. So you have, according to what they say in here about Cramer's rule, the equations are going to, the differential equations are going to be x1 dot, x2 dot. Well, this is x3 dot from here, and this is a Jacobian and a Jacobian. Cramer's rule, where is the derivative, or the denominator? So this is still a puzzle to me anyway, and I was still looking for a way to understand how did these equations appear. We need to derive something, and we take the simple case two functions and three variables. So we'll take as our two functions little f and little g, and we'll take as the variables x, y, and z. And this is the chain rule, the f, the x dt, etc., etc. Now, there's a bunch of atomics going on here. These symbols, big F dot, big G dot, are just names for these equations, so I can refer back to them here in this solve command. And I want these to be my variables in this solve command, so they have to be atomic. Back to normal notation, you can see how natural this looks. So apply the chain rule, solve these two equations for x dot and y dot. Now look at the result that Mabel gives you. This is just ordinary arithmetic. And here you can see Cramer's rule having taken place because there's what appears to be a Jacobian over a Jacobian. And a Jacobian over the same Jacobian here. Now, this minus sign is not counterbalanced by a minus sign here, so you got to scratch your head about what to do about this minus sign. I don't know. You got to scratch your head about it, but I did. This I looked at for forever until it finally I figured out where this minus sign goes. From here, you can see if you define z dot to be the negative of this stuff. And what is that stuff? Well, that stuff's here. It's this Jacobian. And if you define z dot be the negative of this stuff, the negative of this Jacobian. But then you've got to do something here because there's no compensating minus sign, but you can get a minus sign from here if you change the order of differentiation. So let's look at that factor, right? FYGZ, it's this factor. It's this Jacobian. Change the order of integration, of differentiation right here, and you get your minus sign. So now you've got a minus, now you have a way of getting the minus sign out here and the minus sign over here, and you can define z dot to have the minus sign, and then you get cancellation, and x dot is just this Jacobian, and y dot is this Jacobian. So there's the mystery. And until I did that, until I saw how they were manipulating these Jacobians, it just drove me nuts. But it made sense. So now I was ready to do an example. Okay, now I was ready to do an example of this stuff. Let's do a Draghilev example, n equals 2. So let's restart Maple. We're going to use plots, student vector calculus, and student calculus 1. We need some functions, so I made some functions. This is an ellipsoid. This is a plane. I want to intersect these two. There's a solution. It's going to be a circle or an ellipse in space. Implicit plot applied to these two. This is what the graph looks like. It's not the nicest looking graph, but there you go. There's a plane cutting an ellipsoid, and the intersection is going to be this ellipse in space. And there's an intersect plot command that will graph this ellipse. And the actual commands are hiding behind the cell. I showed you how to find that. Okay, so this is the example I constructed, and I wanted to see what happens when I apply Draghilev to this. Let's solve the equations f equals 0, g equals 0. in Maple analytically. Let's see what happens. You get a bunch of solutions. And this is my device for picking out the solutions. There are two x's and two y's. And everything is given in terms of z. And so here are the names I've given it: x1, x2, y1, y2. Everything's in terms of z. Now, why are these what are these four guys? You have an upper branch, so you have an x and a y, and a lower branch, and an x and a y. X and a y, x and a y. So this is what these expressions are giving you. This half, upper, lower, upper, lower. And the graphing commands are behind here, and I've used Maple's space curve command, that's in the plots package, to draw these two pieces of the solution curve. Well, what further information do I want? I would like to know these turning points, this one here and this one here. So I can get them by finding the zeros of the radicand, because it appears in all of these expressions, and outside those two zeros, you're going to have imaginary roots, so there's nothing there. How can I grab this? I could copy and paste it. But if you use Maple's op command, means operands, it will go in here and tear apart this expression and find little bits and pieces called the operands until it gets down to this expression, which is what I'm looking for. Then I want to get its zeros, and there are two of them, so roots command is most convenient. Here are the two roots, and here they are as floats. So I put numeric here, and I get it as floats. So I have a rough idea of where this ellipse lies. And now I'm going to do the Draghilev thing. So I need three Jacobians. I need these three Jacobians. So here they are, Jacobian, Jacobian, Jacobian of these two functions, capital F and capital G. Remember, I defined them here, right? The Jacobians. And these are the Jacobians. Give the order of the variables. And you have to say determinant equals true so that you get the determinant and not the Jacobian matrix. And then every place there's an x, I want an x of t. Every place there's a y, I want a y of t, z of t, because I'm forming these three right-hand sides of differential equations. So this is the first, second, and third, and these are names, dx, dy, dz. They're just names so I can keep track of what's going on. And then I form differential equations. X dot equals dx. Y dot, z dot. And I need an initial point. And you can get an initial point by just going up in here and say, what happens when z is 0? Okay, you get numbers. Okay? And you're solving for x dot, y dot, z dot. You get a solution, and you pick the solution apart. You want x of t, y of t, z of t separately, and I give them names, xt, yt, ct. So here is x of t, this is y of t, this is z of t. So you can use Maple's space curve command to graph that. You get this smooth curve. So there is an advantage of using Draghilev's method here. You get nice smooth curves because differential equations desolve command does a lot of nice work. But what I found was If I apply this to the original request f of x and y, I could not get rid of the t. Everything was always in terms of the parameter t. So I'm going to show you one last thing, how I got around the, the dependence on the parameter t. Our case is the case n equals 1. That's what we've been starting from the beginning. So let's take a look at the formalism behind the case n equals 1. One equation, two unknowns. So it's f of x and y equals 0. Draghilev's method says parameterize x and y as functions of t, then differentiate with respect to t. And by the chain rule, you get fx, x dot, fy, y dot. And it says you're going to get two equations, x dot equals fy, y dot equals minus fx. If we continue with this, we're going to get both x and y as functions of t, and it's very difficult to get rid of that t because we've got to do other stuff with x and y. So you look at these two equations and you say to yourself, well, what if we did y dot over x dot? That would be the parametric form of the derivative y prime of x, and that would be minus fx over fy. Well, right here, you would have a differential equation in x and y. T would be gone. And if you stop to think about that for a minute, what did we really do? We did something obvious from multivariate calculus. D by dx of f of x, y of x, no t, f of x, y of x. Fx plus fy, y prime equals 0, and you solve that for y prime, it's minus fx over fy. This is the differential equation I just realized from over here we could have gotten. Well, took the long way around, but we finally realized how to do this problem. And if you get the solution to this differential equation, even numerically, in Maple, you can go ahead and differentiate g of x, y of x. You get formally g sub x plus g sub y, y prime. And for y prime, you can put this expression, which is an expression in x and y, for which you can solve the differential equation. So what remains is to do an example with this approach. Example 4, I go back to the original problem that was thrown at me in email. So I restart, I need just plots. This is the original function f. I need a point on that curve. And I discovered that 1, 1 satisfies this equation. So that's my point, 1, 1. I'm going to solve the differential equation that I showed up here in the formalism. Y prime, that's what this is, y prime is, this minus here, is the ratio of these two derivatives. Y at 1 is 1. Solve it numerically. Desolve, numeric. I like list procedures, so I get this list of procedures. And y of x is this second procedure, right? So Maple creates this procedure that you can grab, which is what I did here. I got the right-hand side, which is this part right here, the proc part. So the procedure, the numerical procedure that gives me y of x is right here, done in Maple. Well, here's a graph of y of x drawn by this procedure, and you can look at the coding in behind. And it looks to be the right graph, the correct graph. So having gotten this function y of x as a Maple procedure, I look at g. I have to put in y of x wherever I see a y. So that's what I've just done here. I call that new function h. This is what h looks like. You see, instead of a y, you see y of x here and y of x here. Then I want to graph h. Now, this is something that can be graphed uh, with Maple's plot command. Now, let me just quickly show the input there. See, it's a plot, and h is a function of x. So I'm plotting this expression, x equals 0 to 4. That's what the graph looks like. And it resembles the graph that we had obtained earlier. You can go all the way up here to what we did numerically. And compare. Well, that wasn't the example. It's this example here. Right, that curve there. This curve here. So the final step we want to take is derivative of g with respect to x. Okay, so here's g. And we know what the pattern of the derivative is. dg dx, dg dy, derivative of y. And I'm using Maple's differential operator here because this is a function. So differential operator evaluated at x, and y is y of x. And so you get this monstrous expression here. Draw its graph. It's that same bowl-shaped graph that we obtained with more labor here. It's just a question of the frame of in which we drew it. See there, it's 0 to 10, and here it is not 0 to 10. It starts down at 2. Okay, so what's the conclusion that I draw? From this? I should have thought this out better before I jumped into the numerics. The numerics worked, but much better numerics comes from using Maple's desolved numeric functionality. It's easier and it gives better results.